This is a short presentation about our work, surface reconstruction using rotation systems. As the title suggests, our work is covered by two main terms, surface reconstruction and rotation systems. It's straightforward to understand the goal of this work, and you might already be familiar with it. The challenge is, given the input as a point cloud sampled from a surface, how do we reconstruct a triangle mesh to approximate the target surface? With the question in your head, let's introduce the only gold standard in our work first. Everything originates from this Euler characteristic for topological sphere. Chi equals number of vertices minus number of edges plus number of faces equals 2. Specifically, the face here is not restricted to be a triangle, but a closed loop or cycle formed by edges. Fortunately, we have rotation systems help us define the face. It has three operators to traverse all the half edges, or you say the directed edge, in a graph. Imagine a small creature living in the plane, and now a graph shows up. Its three operators will help the small ant to travel every half edge in the graph. Let's move the ant to this edge. Iota h helps the ant turn around. Rho h helps the ant turn to the next road at the intersection point. If we combine iota and rho, we have the tau operator. This operator leads the ant to walk in the counterclockwise. And the closed path walked by the ant is exactly a face as defined. Now we are ready to count the Euler characteristic on some simple examples. Here we have a graph with three vertices and two edges connecting each other. If we apply tau, we will get a single blue face, F1. It is topological sphere, which also indicates a tree always has a sphere topology. If we connect the bottom vertices, it will form a triangle. At the same time, F1 will be separated into two faces. We calculate the chi again. It remains 2. Notice that we are connecting two vertices that belong to the same face. We call it a face split. This operation will never change the topology. Of course, we will introduce another operation that will change the topology. If we have two triangles, it has two topological spheres, which means chi equals 4. If we connect two vertices in the middle, notice here the angle on the left belongs to blue face, and the angle on the right belongs to the purple face. F1 and F4 will merge into one face. By connecting this edge, we increase the number of edges by 1 and decrease the number of faces by 1. Thus, the chi changes to 2. We call the connected edge a handle. A handle will merge different faces by connecting their vertices. We call this operation add handle, and one handle will decrease chi by 2. If we can deal with these simple cases, we can extend it to a point cloud with 100 vertices. We can start with building a k-nearest neighbor graph, KNN graph, of the input vertices. The minimum span tree can be extracted from it. We sort edges in the KN graph by its length in the ascending order, which means shortest edge will be added first. Then we evaluate these edges one by one with this topology test. If it is connecting the same face, it doesn't change the planar topology. Then we allow it to be connected. Till the end, we can reconstruct or triangulate a 2D plane from the point cloud. Similarly, if we can do it in 2D, we can extend it to 3D. And that is exactly what our method does. Again, we have some additional operations for the algorithm to work. Firstly, we use the surface normal of each vertex to define the local plane. Thus, we can again define the row operator to search the next outgoing half-edge. And iota h is trivial, just flips the direction of the half-edge. So the tau operator is well defined. With the same three operators, we can define the face in 3D. We use the same topology test to keep the graph as a topological sphere. Other than that, we need an additional geometry test to remove possible edge intersection in the local plane. This test rejects edges causing intersecting or overlapping triangles. Take the edge UV as the example. We search all the edges within the searchable of radius half L plus L max, where the L max is the maximum length of existing edges. If no edge intersects edge UV, then it passes the geometry test. And here are some ablation studies. T stands for topology test and G for geometry test. You can see if we remove T, possible spurious handles will be added to the final reconstruction. If G is removed, these overlapping triangles will lead the reconstruction to a bad configuration. Up to now, the reconstruction is restricted to be topological sphere. We have another process to reconstruct shapes in other topology. This is done by connecting handles. If the target shape is known to be hygienous, or no knowledge about topology is provided, the handle connection and triangulation stage will be called. Through experiments, we find the graph distance between the endpoints of desired handle is usually significantly longer than the Euclidean distance. Here is the example on the capital A. The blue path is the shortest path between the endpoints of the red handle. By setting a threshold on the distance, we can filter out spurious handles and add the real handles to increase the genus number of the reconstruction. This allows us to explicitly control the topology of the reconstruction. Here is another example on the Stanford dragon. Here is the quantitative result comparing with other combinatorial method. We apply two metrics. One is the vertex reference ratio, which shows how much input information is preserved in the final reconstruction. The other one is the number of boundary edges. This is a general indicator for the quality of reconstruction. Our method reaches the best performance on most test models, including both synthetic and real scanning data. And you can track more qualitative comparisons in the paper and our webpage. To sum up, our method provides the possibility of topology control while reconstructing the surface. At the same time, we preserve most input information from the data source among all the methods. Also, benefit from the graph construction. Our method focuses on the connectivity instead of the scale, which allows us to perform better on point clouds with significant density difference. This case also provides a good scenario where combinatorial method should be preferred. The detailed spiral texture on the trunk is well preserved in our method. And here is another example. For more evaluations and visualization of the result, please refer to the paper and our webpage. You can scan the QR code here to access them. Thanks for watching.